So then should we start?
Yes.
Yeah. So it's my pleasure to introduce you to Roman Stasenko, who will today lecture about short cell-2 structures on simple Lie algebras and Lie modules. Please, Roman.
Okay, thank you very much. I would like to realize my gratitude to the organization of this seminar and the opportunity to make a report. So, as you see on this slide, the theme of our talk will be short SL2 structures on simple Lie algebras and Lie modules. At first, could you please give me some key definitions, or the main fields during all my talk will be the field of complex numbers, as it usual in the algebraic theory. If you replace it with the algebraically closed field with the characteristic 0, especially all the statements will be right. But for me, it's very important to use only the field of complex numbers. So one of the key definition during my talk will be the definition of the Jordan algebra. So the commutative algebra in which the following statements comes true is called Jordan algebra. So as you can see, it's very similar to the associativity, but it's not at all. And this identity can, from this identity, you can derive some special properties of the Jordan algebra, which you cannot see in the associative algebras. So in the middle of the 20th century, there was proved the remarkable theorem of three authors, which connected this class of Jordan algebra with the class of Lie algebras. So it was the theorem of Tits-Kantor-Koeher, and it talks us that there is one-to-one correspondence between simple Jordan algebras and simple Lie algebras equipped with the decomposition of the prime sum, where the first summand is the Lie algebra of derivations of Jordan algebra, and the second it is the tensor product of the algebra SL2 and the Jordan algebra. So the Lie bracket in this vector space is such that in the first summand it is the bracket of the derivations, like the multiplication in the one order minus multiplication in the other order, and the special question is how the brackets is when you take two elements of the second summand. And so the formula in the middle of this slide answer from this question. If you want to commutate two elements of the other summand, you can scalar multiplicate the first A and B from the algebra SN2 and the commute the two linear multiplication, which correspond to the elements of the Jordan algebra. And you can add to this the result of the or the commutation of the two elements from the algebra SL2 and multiply it to the product of the x and y, the product like in the Jordan algebra. So LZ here is linear operator of multiplication. The parentheses are the notion of the scalar multiplication of the Lie algebra, especially the trace or the product of to these operators. So the Tits-Kantor-Koeher theorem tells us that between Jordan algebra and simple Jordan algebra and Lie algebra there is one-to-one correspondence, and it's is the motivation of our investigation, of our talk, and some of the special ways to interpret it, this construction is to look from this theorem using the theory of representations of Lie algebras. So if we look at using this tool, we can talk about special definition. Let S be arbitrary reductive algebraic group, and we will assume that we take the homomorphism from S to the group of automorphisms of Lie algebra G, and these homomorphisms we will be called a structure on G. So if we take here SL2 and have a special special properties of G, like we can interpret such a homomorphism as the representation of group S in the group of automorphism of G. Automorphism of vector space is a group GL, general linear group. And so we obtain the representation of S in G. If we take the SL2, then the theory of the theorem of Tits-Kantor-Koeher will derive from the assumption that, the assumption that we can use only irreducible representations with dimensions 1 and 3. So if we look at this decomposition, we can interpret it as the isotypic decomposition of the vector space G, which the first summoned is the space of SL2 invariant vectors, and the second space is the multiply of the dimensions 3, irreducible representation of dimension 3 with the multiplier G. So this side on the Tits-Kantor-Koeher theorem first was made, as I know, by Ernest Vinberg in his work in 2005, SO3 structures and quasi-elliptic planes, and lately, different kinds of structure were investigated and by special authors. Vinberg was investigate the case when S is SL3, SO3, and we now talk about the case of SL2, and our interest was in the case when we can add to the irreducible representations of dimension 1 and 3 the irreducible representation of dimension 2. So the representation on the two-dimensional vector space of SL2 with some multiplicity at all. So we will call such SL2 structure short, and SL2 structure when the two-dimensional summand is empty, we will call it very short. So the Tits-Kantor-Koeher theorem tells us about the case of very short SL2 structure on the simple Lie algebra. And we now talk about short SL2 structure. It is interesting that in our definitions, we will differ the short SL2 structures and very short SL2 structures. Of course, we don't say that very short is the case of short SL2 structures. They differ very, they have very big difference. So these are two different cases. The isotypic decomposition of our case consists of three summands. The first summand is the G0. The G0 is the subspace of SL2 invariant vectors. G1 is the prime product of the two-dimensional vector space on which SL2 acts, and some other space G1. And the last summand is the prime product of SL2 and the other vector space G2. So our aim is to investigate what is the algebraic properties of G1 and G2. In the case of very short SL2 structure, the G, the multiplicity of SL2, the adjoint representation, the multiplicity of adjoint representation was the Jordan algebra. And how about now the multiplicity of two-dimensional reducible representation and the adjoint one? What are the spaces G1 and G2? So on the algebra G now there are okay, thank you. Sorry. So during the algebra so we can use the commutator on the Lie algebra G, and it is SL2 in the equivariant bilinear map from the prime product of the Gi and Gj to the prime product. According to the Clebsch-Gordan formula, these two SL2 equivariant bilinear maps gives us special commutator relations between the summands. The first commutator relation, if you commutate G0 with one or the others, you can stay in the it. And if you commutate the two last summands, we will go to the G0 and G2, and so on. So from this following relations, as you can see, there is a derivation that you can derive that G0 is a least subalgebra in G. It's a very simple statement. Now, using these commutator relations, we can derive the commutative formulas in the algebra G, which can help us to understand what is G1 and G2. So let's consider arbitrary simple Lie algebra with the involution, which is not identical. Then, as you know, that G is the prime sum of the algebra of invariant points and the algebra on which the identical the involution x not trivial. So the subspace H on which the involution x trivial is a Lie algebra, and the adjoint action of H on some subspace V is effective. If we, of course, consider the simple Lie algebra. According to the to this lemma, for theta is phi minus ID, we can derive that G2 is a sub-algebra, a subspace in the space of all the linear operators on the G1, and G0 is the subspace in the space of all linear operators on G1 too. So if we denote the parenthesis as the trace of the product, and this bracket as the determinant of the matrices 2 by 2, we can give the next formulas. Let's introduce some denotion. We denote by S was such a bilinear map from the product of the two-dimensional space on itself into SL2, as you can see with this formula. And here we can write the computational formulas using the computational relations that you can see on the previous slide. So if you see on this list of formulas, you can find that all of them are defined, but we don't now say about the bilinear map phi and delta. So from the skew commutative for the brackets, we can see that phi is a skew symmetric bilinear map, and delta, little delta, is a symmetric bilinear map. Of course, we need to define what is this what is the this bilinear map delta, big delta. One moment, big delta, but we excuse me, I don't know why it is so. So the big delta. What is the big delta? Skew symmetric bilinear map. But our first aim is to define what formulas can we obtain by phi, delta, and big delta. So let us have some inspection into theory of Jordan algebras. So if we take the A be an associative algebra, the algebra A with the plus is the algebra which we can obtain by replacing the multiplication. Like a vector space is the same as A, but multiplication is different. The here you can see its formula is the multiplication of the operators of the elements from in one order plus in other order divided by 2. So if we replace such a multiplication, we will get the Jordan algebra, and this case is called special Jordan algebra. In the field of complex numbers, there are simple Jordan algebra that not special. It's the simple algebra of Albert's algebra. It's the matrices of the order 3 or the octonions, Hermitian matrices of order 3 or the octonions. And but it is the unique case. Other simple Jordan algebra or the over field of complex numbers are special. So denote by LA the linear operators of multiplication by the element A, and here we can introduce the subspace or the inner derivations of G is the it's a commutation of these two operators of such side, and as you can simply see, it is the ideal in the Lie algebra of all the derivations in the Jordan algebra. So let us call the Jordan algebra semi-simple if there is a non-degenerate scalar multiplication on J such that the following statement is true. This formula. And if Jordan algebra is semi-simple, it is very important for us that all the algebra of derivation is the algebra of inner derivations, and J has the unit. So in our in the case of very short SL2 structures, will be automatically when we talk about simply algebra, and here we need to tell about this this statement because it's very important for our formulation, the main result. So, and for Jordan algebra, the following statement is true. It's J is following criterion of semi-simplicity. If Jordan algebra is semi-simple, if and only if it can be derived into the prime sum of simple ideals. So here are some facts about Jordan algebra which we need to understand the following theorem. So what's about structures? What's about the first goal is to define the in our case, if we commute the different elements of the algebra G and we can obtain that algebra G2, that the G2 is a vector space for us, but it can be considered as a Jordan algebra with the multiplication, as you can see here. When we commute two elements, we here get the commutative binary operation on G2, and this operation gives us the structure of the Jordan algebra on J2. Okay, if we look at the this computational formula, we can see that in the last summand was the bilinear map delta big delta, and so big delta is the in our case of simple Lie algebra is the excuse me this operation this delta is the commutation of A and B. As you can see before, we inner the J2 into the space of the linear operators or on the space G1. So now we can see that G2 is Jordan subalgebra in the Jordan algebra of all linear operators. So this first step to the understanding of the structure of J1 and J2. So the J2 is the subalgebra in the algebra of linear operators on the space J1. And the map delta, big delta is, so as you can see at the bottom of the slide. Of course, here we can obtain that in our case there are no exceptional Jordan algebras. There's such Jordan algebras which can be put into the associative algebra with the classical multiplication, as we can see before. And it's very nice that here there are no such Jordan algebra as Albert algebras. So now we can use the invariant scalar multiplication on the algebra G. As you can see on the algebra G, there is up to non-zero multiplier unique scalar product. We can fix it with such a multiplier, and from Schur's Lambo we can see that the scalar product of the different summands of our derivation of our decomposition are orthogonal to one to each other, and this gives us the scalar multiplication on the space G1 and G2. But on the space G1, the scalar multiplication, which is alpha, is not degenerate but skews symmetric. And on the space J2, the scalar multiplication always non-degenerate but symmetric. So let's denote by the parentheses the scalar multiplication beta, and by the this bracket is the scalar multiplication alpha. So as on the algebra G, this scalar multiplication is not degenerate and invariant, we can see that on the algebra J2 there is a non-degenerate invariant symmetric scalar multiplication, and one can derive from this that Jordan algebra J2 is a simple. The space J1 is symplectic vector space, and J0 is a subalgebra in the Lie algebra of all skew symmetric over the skew symmetric bilinear form operators, and J2 is the Jordan subalgebra in all the algebra of symmetric operators, all these skew symmetric bilinear form. Moreover, the unit elements of the Jordan algebra is the identity operator on this page U1. So in the Jordan algebra, which acts on the vector space, it's not usual that not necessary that the identity element gives identical operators. But here it is this situation. We obtained that G1 is skew symmetric is the symplectic space, yes, with a not degenerate symmetric skew symmetric bilinear form, and the algebra J2 is the subalgebra of the symmetric operators on the G1. So it gives us more information about the pair J1 and J2. So now let us introduce some example of the short SL2 structure. If we consider for the algebra G, the algebra of skew symmetric operators of dimension of the order 4, 1 plus 1 in the basis where the okay, one moment. Oh, here in the basis where G and where the elements of G are matrices of the order 4, 1 plus 1 symmetric with respect to its main cross diagonal. So we must involve the SL2 in the SO for 1 plus 1, and this involving gives us the next basis of SL2, the basis of three matrices E, F, and H, which you can see in the middle of the slide, and which satisfying the special equalities, as you can see here. If we take this SL2 structure on the algebra SL for 1 plus 1, this SL2 structure we will call maximal short SL2 structure, and we can see it. So what is interesting here? Interesting here that we can obtain what are the bilinear maps phi and delta in this case. If we take on G1 linear operators of the rank 1, which satisfies this formula, these two formulas, we can consider two canonical maps, the phi m and delta m. The phi m is in our case, in which we interested in the case of maximal SL2 structure, is such a bilinear map phi and delta, which were in our commuting formulas we see before. I can remember you, but here we saw these two maps phi and delta, and in this case, in maximal short SL2 structure, these two maps here, as you can see at the bottom of this slide, these two formulas can be calculated. So why it is the name maximal short SL2 structure? It's because in this case the subspace J1 and J2 are the maximal in the involving the J2 is the Jordan algebra of all symmetric symmetric operators on the on the symplectic space J1. The J1 is the symplectic space of two-dimensional, and J2 is the matrix is the Jordan subalgebra Jordan algebra of all elements symmetric. As we can see earlier, the J2 is a subspace on this in the general case, but in this case it's the all. It's there is an equality between them, and G0 is the algebra of all skew-symmetrical symplectic operators on J1. So as you see from general case, it is only was the subspace, and in this case it's the equality between them. So here we can calculate always scalar multiplication on J1, as you can see, and for any short SL2 structure with symplectic space, we can now see how the map phi and delta looks like in the general case. In the general case, they are as follows. We need the canonical maps and orthogonal projections on the algebra J2 and canonical orthogonal projections on the commutator of J2 respectively. So pi c is a orthogonal projection on commutator of J2, and pi 2 is a canonical projection on the J2. For the maximal short SL2 structure, as I said, the phi is equal to phi m and delta is equal to delta m. So now the last question for us to this construction is what is the object which is one-to-one correspondent to the short SL2 structure. As you can see in the previous case, when we talk about very short SL2 structures or the construction of Tits-Kantor-Koeher, we see that the one-to-one correspondence was between simple Jordan algebra and simple Lie algebra. And what in our case it is. So let us gives one step away to talk about this in the future. Let us consider the reductive Lie algebra, and let R be faithful orthogonal linear representation on the some vector space V. So we can on the space of the prime sum of H and V gives a structure of Lie algebra. And always, if we consider Spatch 4 linear form, which consists of the Lie brackets and the scalar multiplication, we can see that the operation as we defined above gives us the structure of Z2 graded Lie algebra if and only if this form of this full linear form has the similar of curvature tensor that in turn is equivalent to the fulfilling the Bianchi identity, as you can see. And we can think about it and this Bianchi identity is not occasionally in our case because in our case the K is covariant curvature tensor on symmetric space G frac H at the base point of the neutral element, where G, the big G, is such a complex group that the Lie algebra of the G is G, which we now use, and the H is a Lie subgroup such that the Lie algebra of the group H is as we see, reductively algebra H. So the Bianchi identity is not occasionally here because it's connect with the covariant curvature. So if we return to the consideration of short SL2 structure, we can assume that the H is the prime sum of the J0 and J2, and V is the last sum on J1. If we write the full linear form as they see on the previous slide, we write the Bianchi identity, we can rewrite it as the simplicity, as the symmetry of such full linear form on the vector space J1, using especially with delta and phi, using delta and phi and scalar products that we introduced earlier. So here we are ready to introduce the object that is gives us one-to-one correspondence in the case of short Lie algebras. Let J1 be a symplectic space and J2 be a semi-simple Jordan subalgebra whose unit is the identity operator of the space J1, and J0 is the subspace of the symmetric operators on J1, and it is a reductive Lie subalgebra of that the commutator of J2 involved in it, and if we and very special case that if we looks at the adjoint representation of the G0 of the G0 on J2, we will get the action. Yes, all the commutators lies in the algebra J2. So J0, or using the adjoint representation, acts on the J2. Then with these assumptions, we will get the following decomposition of J0 is the prime sum of the commutator of J2 and the ideal I0, which acts on the J2 by 0. So so if we compute I0 with J2, we will get 0. In the case of very short SL2 structure, we will see that the J0 is not another that commutator of J2. And here we obtain that there is another special ideal of J0 which we can get in our object. So in the case of very short SL2 structure, J0 will get from the Jordan algebra, and here is not the same. Here is not. It is can be fully get from the Jordan algebra J2. Of course, we need some more component. We need J0 equivalence surjective map from the from the Cartesian product of J1 on itself to the this ideal I0. Especially we need that this general equivalent surjective map satisfying the following identity. So as symmetry over the action of Jordan algebra. So let us introduce two maps, delta and 5, using these formulas. So phi1 and phi m and delta m are the as you can see before yes, and delta is the composition of delta is the sum of the two maps, delta 0 and delta c. And delta c. So you can introduce the special term. The quads J1, J2, G0, and delta 0 is called symplectic Lee-Jordan structure if the trilinear map F, given by the formula, is symmetric. So as you can see before, we are talking about the symmetricity of the four linear form, but this free linear form can be derived from it if we use the special properties of the scalar product, its invariant properties. We can derive it from the previous formula, and this equality is very important. That these four elements are called a symplectic Lee-Jordan structure, and this is such an object as we need. Of course, we will assume that the scalar multiplication on algebra of symmetric operators of the symplectic space and the symplectic operators are defined with respect to formulas described above. And this Lee-Jordan structure is called simple if the Jordan algebra J2 is simple. So the simplicity is very simple way. If we take simple Jordan algebra, we will get the simple symplectic Lee-Jordan structure. As you can see, the situation now is very very different from the case of very short SL2 structure from the Tits-Kantor-Koeher construction. Here we need to introduce four elements. As you see before in the Tits-Kantor-Koeher theorem, there is only one element we need to introduce, the Jordan algebra, and the construction can be derived from it. And now, if we consider short SL2 structure, not very short, the situation changes. So in the previous year, I proved such a theorem that there is a bijection between simple symplectic Jordan structures and simple Lie algebra with just short SL2 structure, as you can see here, and the structure of the Lie algebra on J is introduced using these commutational formulas. So phi and delta are introduced as the given above formulas. Here you can see it. And other objects we see before. So it's the analog of the Tits-Kantor-Koeher construction. And in this case, there is very comprehensible answer that we need to introduce 4 elements, the special map by linear map, the Lie algebra, reductive Lie algebra, the Jordan algebra, and the vector space symplectic, which are connected to each other with special identities. So it's very, very well, but the reason why it is so, we can't we can't vanish one of them. So we need and vector space and Jordan algebra, and of course we need Lie algebra because we can't introduce it without using only Jordan algebra. And of course we need a special map to get a case to get this identity. We need such a delta 0. So the main reason why it is so is the Jacobi identity in the on the Lie algebra G, and to make it true, we need some special conditions on the elements of our object, on the 4th elements of our object. These conditions are on the previous slide and here. So now let's talk about the next step. If we have a bijection theorem, we must say about the classification of all such an objects. So if we classify all the short SL2 structures on the simple Lie algebras, we get the full classification of the simple symplectic Lie Jordan structures. So as you can see on these slides, this was made. You can see on the 3 columns, 3 last columns, the the elements of this symplectic Lie Jordan structure, which correspond to such a short SL2 structures. As you can see on the second column is the diagram of the short SL2 structure. As you can derive, you can get this diagram if you look at the adjoint action of the Lie algebra on itself. If you see on the definition of short SL2 structures, it gives us that the isotypical decomposition consists only from the irreducible representations of dimensions 1, 2, and 3. So if we take the element H of SL2 triad, the basis of SL2, as you can see, one moment here, the element H. The element H with the adjoint action of the algebra G gives us the SL2 structure if and only if the irreducible representation only with dimensional maximum 3, and so the homogeneous subspaces of these elements gives us the root subspaces only with the element 2. In our case, we can get only a root subspace with the multiplicity 2. So if we take the highest root of our algebra, we can see that on this algebra it can be gives us only the number 2. So on the highest root gives on the element H is only the number 2, and this is very, very strong restriction on the evaluation of the simple roots on the H. So they can gives us only the number 1, and in SLN there are 2 such simple roots. In SO2N there is 1 such a simple root that gives us 1 on the element H, and in other cases were considered at all. And here you can see the classification of short SL2 structure on the special Jordan-Lee algebra, exceptional Jordan-Lee algebras. As you can see, in our case, except J2, there are 2 such as different SL2 structures. One gives us the trivial Jordan algebra in every case, and other gives us not trivial Jordan algebra, or the so-called Clifford type as the subspace of Clifford algebra. So here you can see the denotion of Y from P1 is the vector space of irreducible representation of the first weight of the algebra E8, of the first weight weight. By S we denote the representation of the SO of the algebra of orthogonal operations, and here you can see the tensors of 3 of the order 3 with the trace 0 on the 6-dimensional vector space. So the full classification you can see here. So by S is the spinor irreducible representations of the skew-symmetric Lie algebra, skew-symmetric matrices of the bilinear form. So and the last part of our talk, say about the further steps in our investigation. So we can see that short SL2 structures on the simple Lie algebras were investigated, and we will get such a comprehensive answer. But can we use all this theory to the theory of representations of Lie algebra? Of course, you know that the theory of representations of Lie algebra is very widely investigated and has a very remarkable theorems. But this remarkableness is not in the case of Jordan algebra. The representation of the representation theory of Jordan algebra is very poor. For example, you can see that there are only infinite number of irreducible representations of every simple Jordan algebra of the field of complex numbers. And maybe if the theory of short SL2 structure gives us a connection between Lie algebras and Jordan algebras, we can expect that the theory of representations with the tool of short SL2 structure of Lie algebra gives us a tool to investigate the representations of Jordan algebra and connect them to each other. So this tool comes true if we define a homomorphism from group SL2 to the group of general linear of the vector space or the Lie model SL2 structure if this equality is true. So this equality is a connection between the SL2 structure on the Lie algebra and SL2 structure on the G module. It gives us the connection between them. We need to prove theorems and investigate them. So this definition is the key to the last part of our talk and all the short SL2 structure on Lie modules. As in the case of Lie algebras, here we can see the following decomposition. The isotypical decomposition. If we consider the SL2 structure on the Lie module, as a typical decomposition gives us such a formula. And of course, the general case of this formula with such a or with all assumptions is very hard to investigate, and we need some special cases, very simple case to investigate. Let us investigate the most simplest case where in this formula there are only two irreducible representations of SL2, the one-dimensional and two-dimensional. And in this case, we call the space U short G module at all. So if all of the multiplicity spaces are zero.
So Roman, you're already over time, so you probably should think about finishing.
Yeah, of course, I finish. So if we give us such a way, we can answer the same questions. What is here the object that is one-to-one correspondent to the irreducible representations, and of course, in the space of in the case of very short SL2 structure, the answer will given in the paper of Kantor and Spies in 2005, and here you can see the answer. So if we take a simple Lie algebra with very short SL2 structure and give it irreducible short Lie module, it's one-to-one correspondent to the irreducible J2 module. And what is J2 module? It's such a module, we can see the linear map from the J2 algebra of endomorphism with such a property, and so we will call the space V the linear Jordan J mod, special Jordan J mod. So the here answer is very simple, and a few words about the our case. In our case, the answer is not so simple; it's hard, but the very interesting thing that in this case we need to give the structure of J model, and here we need only the Lie algebra. We need the subspace W and the map from the J1 to endomorphism of W with the special restrictions. As you can see, we need to call them action formulas. So the answer here is such hard that there is one-to-one correspondence between this SL2 structure on the simple algebra and its Lie model, and the such a object as we called the irreducible Lie Jordan module. What if the algebras, if the map sigma satisfies these formulas, we call such a vector spaces Lie Jordan module. So the answer here is a bijection theorem, and here you can see the classification of all these cases and the references from which I used to investigate this. So for me is the end. Thank you for your attention.
So, thank you very much, Roman. And now, if anybody have a question, remark, or suggestion, please. Yeah, Alberto.
Yeah, just thank you very much for the talk. I would like to add a comment that when you consider a very short structure on a Lie algebra, the pair consisting of your J2 and J1 form what Allison called a J-ternary algebra.
Yes, I know this answer. If we take the algebra, not the SL2 but SL3, we will get the Allison algebras as right in the Vinberg so paper in 2005. Allison algebra arise there when they take SL3 structures, but not SL2. Yes.
No. You get structurable algebras with SL3, but with SL2 and very short structures, SL2 structures, you get the so-called J-ternary algebras that were defined also by Allison. these are a different kind of algebras.
Ah, okay, thank you.
Yes.
Mhm.
So essentially, I guess which Alberto is saying that you get a sim of 3 graded Lie algebras, or when you say ternary, it's just because there was this,
Ternary,
graduation, ternary graduation.
No, these J ternary algebras consist of a Jordan algebra and a special module for the Jordan algebra with some extra properties, which are essentially the properties that appear in the talk, relating J2 and J1.
I also have a couple of questions. The first one is just this classification of SL2 structures. It's just nothing but describing SL2 inside the joint form of Lie groups. I mean, it seems you were calculating root systems and centralizers in there. Is not that from Borel set or a classical one about maximal subgroups?
of course,
Or-
of course, I know about this classification, but I don't know about it when I do such a day. But in my paper, there is a special references to this classification. Of course, you can obtain this classification from the from this. Okay, of course.
And then my second question, well, I don't know if this is really a question, but I missed the point where you somehow relate with the curvature of a symmetric space.
Yes, it's here. I can.
Yeah.
Here.
Yeah.
Yes.
So I didn't get it right, but I remember that speaking with Otmar, he somehow came to Jordan algebras because his PhD thesis was about symmetric spaces. So is there any relation like that, or I'm sorry, I missed how the curvature of the symmetric space show up in here. So I was wondering if there is really a description of this curvature in terms of Jordan algebras, like Otmar Loss did in his PhD thesis, right? He started studying symmetric spaces and then he ended up studying Jordan algebras. So I don't know whether you are going the other way around or have nothing to do at all, and I missed the point.
So I really don't know about this correlation, but here the such a special way that that there is a faithful orthogonal linear representation on the Lie, and so if we take this symmetric space, you can calculate that the covariant curvature tensor is looked like this. And the Bianchi identity holds in this case, but
Okay, I mean, it's just curiosity.
Okay.
So more questions or comments? So if not, let's thanks again the speaker. So thank you very much.
Thank you.
And see you all next Monday in the next seminar. Bye-bye.